So, we've talked already a bit about causality and scientific reasoning. Now, we're going to dig a little bit deeper into scientific reasoning in a discussion of the topic of inference to the best explanation, hypothesis testing, experiments and predictions, and then lastly, distinguishing science from superstition. Let's get started. So recall that on an individual basis, that is, in our daily lives, we consistently use, although we don't always use correctly, the inference to the best explanation. And indeed, even in formal environments, that is, in a professional scientific environment, it's not always the case that inference to the best explanation is used to its maximal effect or used correctly. So what we want to do here is just talk about what it is that's happening when we make an inference that we take to be the best explanation for a phenomenon that we have observed. So when we want to explain what it is that we're observing, we make an inference in the mode of what is known as abduction. So this is historically distinct from inductive reasoning. At the same time, abduction and induction are both versions of experiential reasoning or empirical reasoning. Typically, we've today collapsed abduction and induction into a single process of experiential or empirical reasoning. The process known as an inference to the best explanation involves reasoning from the premise that a hypothesis would explain certain facts to the conclusion that the hypothesis is, in fact, the best explanation for the facts observed. So what would be involved in such an inference? Well, what would be involved would include historical data, contemporary knowledge, and the likelihood that the conclusion is correct. When we make an inference to the best explanation, part of what it is that we want to include is working within the parameters of standards. So we want to make sure that the inference to the best explanation and the theories that are meant to be the result of rigorous testing include standing up to severe and repeated hypothetical or hypothesis testing. It's also the case that the explanations have to be coherent and effective. In addition, the predictions based on the testing and the explanations are correct. That is, that they win out more times than they don't. And in fact, it's not just the case that we're talking about the predictions winning out more times than they don't, but that the margin of error is incredibly small for those predictions not panning out. And then lastly, that the theories help us discover new facts about the world. So one of the ways in which experiments proceed is in terms of controlled testing. That is, there is an experimental group and a control group. So the idea behind having an experimental and a control group is to eliminate variables that might otherwise explain what it is that you're trying to prove. So the idea with an experiment is to determine whether or not the hypothesis in question is correct. So suppose, for example, we're talking about an experimental drug. It's important to understand what the demographic is, not just that the experimental drug is being tested out on people who should benefit from that drug, but it's also the case that other variables in that demographic are understood. And then also there is a control group, that is, the same type of subject is enrolled in the experiment, but they're not going to receive the drug, the experimental drug. so that there is ideally a clear indication of the drug's efficacy. So all of this brings us to another way of thinking about causality, that is a more general idea of determining that, for example, a specific drug relieves symptoms or a specific drug cures a specific disease or disorder. So we're looking at a correlation between the purported cause and effect. We're looking at making sure that the purported cause precedes the effect, that the cause is in proximity of the effect. That is, the cause should not be considerably removed from the effect, which weakens the possibility that the purported cause really is the cause of the effect in question. There is also a set of necessary and sufficient conditions that can be understood as holding every time we say that the cause in question is the cause of a certain outcome. And then finally, alternative explanations should be ruled out. As I mentioned in, I think, a previous video, more on necessary and sufficient conditions will be discussed in a separate tutorial. Take a look at this slide, in which each of the criteria for determining causality is explained. And then we'll look at some examples. Let's look at some examples. We'll also take a little bit of time to talk about sufficient conditions, necessary conditions, and joint necessary and sufficient conditions. Here is a short excerpt, I should say, from a CNN article. The quote reads as follows: "About 1 in 6 unemployed workers are addicted to alcohol or drugs, almost twice the rate for full-time workers, according to the government's National Survey on Drug Use and Health. The survey shows that 17% of unemployed workers had a substance abuse disorder last year, whereas 9% of full-time workers did so. The numbers are self-reported and therefore could be even higher in reality." So all we get here is a correlation between unemployment and drug use. What we're looking for when we're looking for causation is not mere correlation, but an explanation as to why, for example, people are taking drugs, or why, for example, people are unemployed. So what you'd want to do, instead of simply finding a correlation between two events, is determining which is said to be the cause and which is said to be the effect. And then working to, by way of, let's say, experimentation or some other less formal means, to determine whether or not the hypothetical cause is in fact a legitimate, plausible cause of the effect you're trying to explain. In this case, is unemployment the result of drug use or vice versa? Again, right now, from what I've given you, all that we have is correlation. Next, here is an example of proximity. So from a government website, I've borrowed the following: methods of drug administration in order of fastest to slowest central nervous system response. So from intravenous all the way down to rectal drug administration, we get the fastest central nervous system response. So depending on what one is trying to treat, and depending on how fast they need for the treatment to take effect, they will use the relevant administration. Now let's look at, respectively, sufficient conditions, necessary conditions, and joint necessary and sufficient conditions. Remember, what we're talking about here is a sufficient condition, or a necessary condition, or a joint necessary and sufficient condition as a cause of a given effect. So one cause is known as a sufficient condition, which is an event that guarantees or produces another event. So, for example, I can say that a sufficient condition for me to have something in my stomach is eating a potato chip, right? If I eat a potato chip, then I do have something in my stomach. We talk about sufficient conditions as antecedent or prior to their effects. In terms of conditional claims, we have the following. Sufficient conditions are said to be in the if or antecedent position of a conditional claim. And then an example. If I have a headache, then I take an aspirin. So you might say, well, it's not a guarantee that you'll take an aspirin, but let's say that the formation or formulation, I should say, of the sentence is such that having a headache is said to guarantee taking an aspirin. A necessary condition is one without which another event will not obtain. So in terms of the if-then relationship, the necessary condition always goes in the consequent or the position after the word then. We can say, for example, that oxygen is a necessary condition for a human to live. We would not say, on the other hand, that having oxygen guarantees or is a sufficient condition for life, for human life, right? It's necessary, but not sufficient. And then we have an example. Without my diabetes medication, my blood sugar levels won't be manageable. And here, diabetes medication is claimed to be a necessary condition of maintaining blood sugar levels or managing blood sugar levels. Lastly, a joint necessary and sufficient condition is said to be a condition which is both necessary and guarantees that another condition obtains. So, for example, we can stipulate that completing nursing school is an educational requirement and is a guarantee of having a nursing degree. Lastly, when we're thinking about determining a causal relationship, one of the things that we want to do is rule out plausible alternative explanations. So take, for example, a case in which, and I hope this doesn't happen, or it hasn't happened, but you've just completed a long shift and find that that your car is missing. Where you parked your car is now empty. So what you want to do is explain its disappearance. And the question is, what's the most plausible explanation for the disappearance? And once you've narrowed down the implausible from the plausible, the question is, how do you rule out plausible alternative explanations so that you can focus on what you take to be the causal explanation for, in this case, the missing car. In terms of more formal procedures, the question is, which is most likely and why? In other words, why are other plausible explanations not taken to be the explanation for the event? Let's return now to the context within which this set of examples takes place, and this is the context of developing a hypothesis, testing a hypothesis, and accepting a hypothesis as an explanation of events, and then using that hypothesis to make a prediction. What are the conditions for a solid prediction? Well, the prediction should be verifiable, should not be trivial, and there should be a logical connection to the hypothesis. And this logical connection is most commonly the empirical connection, but it can also be a deductive connection. So take a look at the examples below in the definition of a verifiable prediction and see what you think about each of the hypotheses in terms of the requirement that the prediction be verifiable. Recall that when we're talking about a verifiable prediction, we're talking about an empirically observable event, directly or indirectly. The predictions also can't be non-trivial. In other words, they have to have a certain significance. So the example here involves Haley's hypothesis with respect to explaining what's happening with events that were observed, astronomical events observed. So there is a situation in which a series of astronomical events have been noted, have been observed, and Haley's hypothesis is that rather than there being different comets that account for each of the observations, instead it's a reappearance of a cyclical comet. So what we get from this particular example is the idea that another appearance is going to occur, and the prediction includes when that appearance will occur. This is considered to be a non-trivial prediction because if it turns out to be correct, it is a prediction that on which scientists can rely. So we have the following. Haley noticed a pattern, he made a conjecture, and from the data that he collected and the background knowledge, in this case Newtonian theory, that he relied on for his explanation, he calculated the next return of the comet, which led to a specific prediction. So all of the foregoing is a foundation or a backdrop against which you can contrast superstition, right? When we're talking about scientific knowledge, we're talking about claims that are reliable, claims that are derived from and tested by experience, and that involve a level of empirical rationality. In other words, when we're thinking about explanations for events, we're thinking about what seems to be the most reasonable within the context of what's already been observed. So we can say, for example, that although someone might be a theist, it's not the case that a theistic belief is going to be able to explain empirically phenomena. In other words, evolutionary theory better explains what we observe than does an intelligent design theory. This is not to say that there are no scientists who are also religious believers. Plenty of them are. But it's not the religious belief that drives the scientific enterprise. The religious belief is a separate facet of that individual's life. So that the scientific beliefs are beliefs grounded in what the empirical evidence shows. So it is true that various types of superstition, and by the way, some people use the word superstition to mean something negative, and some people simply use it to refer to that which is not scientifically verifiable, right? But the allure of superstition is certainly great. It seems to be part of a human being's psychological structure. That said, the rigorousness and careful attention to detail required by the scientific method is much more reliable than non-rational or, if you will, irrational beliefs. All right, I hope the last of this two-part overview of causal and scientific reasoning gives you a basic set of concepts that you can enlist as you are practicing with the material in chapter 14.